is Kianté Brantley from the Kempner Institute and Harvard Seas, who has done really good work on reinforcement learning. Today, I believe he will be talking about language models and efficient reinforcement learning. So take it away.
I am Kianté Brantley. Thanks for having me. Yeah, I changed the title of my talk because there's this. I wanted to kind of spruce it up a bit, and this was loosely inspired by the title of Dylan's recent paper. So the title of my talk is "The Power of Resets: Learning Better, One Reset at a Time." And so, a large language model is a deep learning model trained on massive text data sets to understand and generate human language. Right? It's a very simple idea, but it's having a big impact on the world today. And so the question I've always been interested in since the start of my PhD is the following: how does different objectives shape language model behavior? Very simple question. And so to get some insight into how we're going to think about this, let's go through some of the most recent papers that have come out, and we'll start building momentum up into this direction of trying to address this question. So there was a paper in 2022 from OpenAI, Learning from Human Feedback. And I'm color-coding some of the plots to make it easier to interpret what's going on. So the dashed line, so what I'm showing here on the x-axis is model size. On the y-axis is human win rate against a supervised fine-tuned model at 175B. There are three different training regimes. There's pre-training, supervised fine-tuning, and RL fine-tuning. In green, there's pre-training. The dashed line is human win rate against the supervised fine-tuned model with itself, which is 50%. And we saw that when you do RL fine-tuning, no matter the model size, it always performs better than all of the model sizes of doing supervised fine-tuning on pre-training. Right? So that was cool. And then most recently, we've seen learning from reasoning with language models, where I'm taking a quote from the blog. It says, we're introducing OpenAI's O1 model, a new large language model trained with reinforced learning to perform complex reasoning. So again, we see that RL is having such a big impact on training language models. And so what is the objective function that we're optimizing in both of these settings? The objective function looks like this. We would like to maximize some reward subject to this minimum deviation, meaning we don't want to move too far from this reference policy because this reference policy is this pre-trained model that has good representation. But there is some reward function. If we can define it, then we would like to optimize it well, right? But if you've done RL, not in language, but in other settings, you know RL is hard. There's sparse reward or delayed reward, there's exploitation, there's credit assignment problems, there's sample efficiency, but there's other problems like hyperparameter tuning. There's a lot of things that go to make RL work really well for problems. And if we believe that RL is going to help us in language, the question is, can we get inspiration from how we solve some complex problems in another domain for RL? So I'm going to go to Montezuma's Revenge. So if you've been in the RL space, you know that Montezuma's Revenge is this classic problem where exploration is very hard. And so let me walk you through why it's hard. Solving the problem is hard. So let me walk you through why if you don't know the domain. So you have an agent, and you only get reward if you kind of go to key parts in the state space. So in particular, this agent only get reward if it actually hits the key. But there's lots of ways to die. If it goes off the ledge, it'll die. There's plenty of ways to die, and every time you die, you don't really get a reward signal at all. So a very sparse problem, right? And so let's assume that our agent goes through this whole process and it climbs up the ladder and it's very close to getting the key. Meaning it's very close to getting a reward. But instead of going towards the key, it goes right? And it falls off the ledge and gets a reward of 1. Well, that entire long trajectory was very informative. It was very close to the key. It just made one wrong decision. It fell off the ledge, got a reward of 0, and now the gradient update for this is 0. We learned nothing from this, right? And so there was an observation in 2018 and 2019 was that if we're able to take advantage of environmental properties, such as the environment is deterministic and the ability to reset, then maybe we can take advantage of that trajectory that had, potential to give us a good reward signal. And the question is, if this was very helpful for solving Montezuma's revenge, can it help us to develop algorithms for language models, for RL for language models, in order to sort of help us develop more algorithms that's able to improve, increase efficiency, help us get higher reward, and solve tasks better. And so the question in my talk that I would like to address is how can we develop efficient algorithms for solving the maxent RO objective, assuming access to environmental resets. And so the talk is broken down into 3 parts. We're talking about resetting with a reference policy, resetting with demonstration data, and then resetting with our current policy. And at the moment, I'm not telling you exactly what are for these 3 regimes what they're going to help me with, but we'll figure it out as we go. So resetting with the reference policy is going to help us boost exploration. And so what is this reset property in the context of language? So reset is going to allow us to roll out our policy from partial sentences. And so why is that helpful? Because we're going to be able to inject additional sources of information into our experience collection. So reset in language looks something like this. I'll sample a prompt from my data, and I'll sample a response from my policy, and I'll score that, and I'll get a score for this prompt and this prompt and response. And because the transition function is deterministic, that means that I can reset, right? I can remove, delete words from my sentence, resetting back, and I can deviate and sample a continuation response with my policy. So that's cool. And I can score this deviated sentence. Now, if I put all the pieces together, the first part I'm going to call the roll in, and the second part I'm going to call the roll out. So the roll in is going to help me find good states to learn on. It's going to help me with exploration. Yeah.
How do you get that reward here? Should I clear the end and then basically roll back what you want? Because I'm assuming that
The reward is prompt plus response. So I give both these things to my reward model, and I give a score. Yeah. So my reward model could be a verifiable reward. My reward model could be a preference reward. However you define your reward function, I assume I have this, and I just take my prompt and my response, and I give it to it, and I get a score out. Make sense? Okay. So the roll in is going to help me find good states to learn on. It's going to make exploration easy. The roll out is going to help me score those roll ins. Right? And the thing I wanted you to pay attention to here is that the roll in and roll out could actually be different policies, right? And so in this paper, Learning to Generate Better Than Your Teacher, we study the different roll in and roll out schemes. Now, for the context of this talk, I'm just going to focus on the one that was the most promising. But depending on your setting and your environment, depending on the task that you're trying to solve, different schemes can actually work better for you. So in this roll in and roll out scheme, we can think about how PPO looks. So for PPO, the roll in and roll out policy are the same, and PPO doesn't leverage sort of problem-specific structure. Because the roll in and roll out policies are the same, it's not going to take advantage of resets. And what PPO does is it samples a prompt from the data, and you score this prompt and response from your policy with your reward function. And so the thing I want you to pay attention to is that in the objective function for maxent, we have this constraint that we want to say near pi ref. So it's very natural to say, what if we put pi ref as our roll in policy? Because we can roll in with states that pi ref visit and learn how to sort of extrapolate from those states that pi ref gives us. And so this algorithm we're going to call PPO++. So for PPO++, we're going to sample prompts from a mixture, which sometimes we'll sample prompts from our original data set, and with some probability we'll sample prompts by rolling in with this reference policy. And so the idea is that if the reason why we're interpolating, because if this reference policy is bad, at least we're sampling from our original prompts. And so we know that we can at least do better than that reference policy if it's bad. But if it's good, it's going to help speed up learning for us. And then we'll score those actions we'll score that prompt and response pair that we got with our rewards function. And intuition is that we're just enriching our initial state distribution, sort of helping boost exploration. And so the theory of PPO++ looks like this. Let's assume that pi star is some high quality policy covered by pi ref. Because otherwise, if we don't have a policy that's better than the policy of pi ref, why do we have this KL regularization there? We have to assume that there is some policy that we can achieve that's better than pi ref, and pi ref has coverage over it. Because if it doesn't have coverage over it, then having that KL regularization there is not going to sort of help us much. So what I'm showing here is the performance gap between this high quality policy and the policy that we have. So there's two quantities that I want to pay attention to. The first is epsilon. So epsilon is assuming that we have one-step local improvement of pi t is small, meaning that our policy is doing very well with respect to the advantage function here. So if we're doing very well with respect to the advantage function, then this epsilon is very small. And the second thing we're going to assume here is sort of bounded density ratio. So we're going to assume that pi ref has coverage over this high quality policy. And so we ran experiments in the Reddit TLDR task, where you're given a post, such as like the Reddit subreddit, the title, and the post, and you're given sort of human labels where the model generated a potential TLDR, and like humans sort of rank these things. So given this data set, where the data set is composed of 210,000 prompts, 117 prompts come from human labels, and 93,000 prompts come from human preference labels. And so the 117,000 prompts from human labels we're going to use to do RL fine-tuning. And the 93,000 prompts from human preference labels we're going to use to do pre-training with the reward model. And so the results look like this. So what I'm showing here is GPT-4 win rate. So what we do is we train these models, and then we give the model a prompt, we sample from it, and we take the reference response and the model response, and we ask GPT-4 which one is better and explain why. So I'm showing three baselines that we compare to. Just the reference model, compared. The reference model means like the reference base model. So just the base model generate response compared to the reference data, the reference response in the data, and see which one is better. Best of n, PPO, and we see that PPO++, there is some improvement over PPO, meaning that using this reference policy for exploration is sort of helping us improve our reward function. Or helping our policy sort of improve its performance. So in summary, PPO++ does not leverage, PPO doesn't leverage any problem-specific structure. The ability to reset is a unique property of MDPs for language models. And PPO++ is a simple algorithm that leverages resets. There's a swapping of PPO++ and PPO here. Sorry about that. Are there any questions on this part? Does this make sense? Yeah.
When you're deploying an LLM in the real world, right? Is it a good idea to kind of leverage problem structure, because the problems that you face will be very diverse?
The problem structure I'm leveraging here is the structure of the MDP.
Okay.
Of the MDP. So so the MDP is deterministic and it's like resettable. That's all. That's the only two things I'm taking advantage of. Just of the MDP, not of the task itself. Because task by task, they're like different. There's a lot of different things that happens across tasks, but just the MDP resettability and deterministic is the thing I'm taking advantage of. Yeah?
Try to extrapolate instead of interpret.
Could you elaborate?
Can you kind of getting further in the instead of getting close, like medium,
I see. Yeah, no, I haven't tried that. That's a good point. Any other questions?
Why does PPO plus plus just have a very small improvement over PPO?
Yeah, that's the right question. I have an answer for that. Okay. Yeah, that's a good. I have an answer for that. Yeah, we had the same question. You're gonna like this. Okay, so can we improve the performance of mixing by mixing in a different distribution? So there's a very subtle thing that's going on here. I'm showing GPT-4 win rate of ref, meaning like my reference policy, the policy I'm starting with, and it's 44.29%. That means that the human data is actually better than like my pre-trained policy, right? So if that's the case, then we should probably do something slightly different, right? And so at the moment we talked about resetting with a reference policy, but now I'm going to talk about resetting with this demonstration data, right? And again, if the catch is that like if the demonstration data is better, like the outputs from the demonstration data is better than outputs that's coming from my policy, then maybe I should reset with that, right? And this should help boost exploration, which should help improve my policy's performance. And so the question here is like, can we improve performance by mixing in a different distribution? And the insight is that if the demonstration data or some other distribution is better than the current distribution I'm mixing in with, if I use that, does my policy performance go up? And so again, let's go to this reset properly to make sure we're all on the same page about what's going on here. So the observation is that most text generation tasks have offline label responses, and we would like to sort of take advantage of those if we see that the responses are higher quality than the response I'm getting from my pre-trained model. And so now I'll sample a prompt and response from my data, and I'll reset using that response data, and I'll sample a continuation from the response data using my policy. And I'll score that prompt and response with my reward function. And now the question is, under this setting where you can reset with demonstration data, not reset with some preference, some pre-trained model that you have or some reference model that you have, like what happens here? So we have a paper called Dataset Reset Policy Optimization that answers this question, because we were curious just like you were curious about what happened and like what's going on here, right? So again, if we go back to this roll in and roll out scheme, PPO doesn't leverage any problem structure. And problem structure in this case meaning structure around the environment. Like the environment is deterministic and has resetability. And PPO just samples prompts from the data and it scores those prompts and responses with some reward model. The reward model could be a verifiable reward model, it could be a personal reward, it could be whatever reward model that you have. You give it the reward model, it'll score it. And now this idea of called a DRPO will sample prompts from a mixture. Now this mixture, sometimes it will just sample the prompt from the data, or sometimes it will sample the prompt concatenated with some partial response that's in the data. And then we'll roll in with this mixture that's coming from the data, and then we'll roll out with our policy. And we'll score this roll in and roll out with our reward function. And again, the idea is that we're enriching the states by boosting exploration because we're putting our policy in really good states to learn on, right? We're like basically shortening the horizon so that you're very close to a reward. And because we're sampling random points in order to like roll in and roll out, we know the policy is getting good coverage over possibly good states. And because we're using we're mixing the initial prompt, that means that it's actually learning from the beginning as well, just in case the roll-in data is bad. Does this make sense? Any questions? Yeah, I was trying to like condense notation. DX is just saying like there's a data set. I'm just taking the prompt from it. And then the mix is saying there's a data set and I'm taking the prompt concatenated with the response. And I could have like tucked in more notation, but I was like, maybe I don't want to do that. But that's basically what I'm saying. Like half the time I'll sample a prompt, other half the time I'll sample a prompt concatenated with the response, and that response I'll decide how much I want to roll in with that thing. Make sense? And so informally, the theory of DRPO looks something like this. We're using MPG as a policy optimization oracle, and DRPO, similar to like PPO, is able to learn a policy is at least as good as a policy not covered by the reference policy now, but covered by some offline data. And there's like two assumptions we need to make here to like make the theory work out nice, is a trajectory-wise density, but also a state and action sample-wise density. For PPO++, we just needed the state action sample-wise density, but we need both for DRPO. And again, we're going to go back to the experimental setup that we just talked about for PPO++, because we're very curious to see that if you have like data that's sort of better than data you had before and you mix in that thing, what sort of happens? So we're back in the TLDR setting where the task is to write a TLDR. The example post, we're like giving some example posts and we're giving human labels. And the results look something like this. So again, we're comparing to two, well now it's DRPO, so we're comparing to like two baselines in our previous algorithm that we had. And so in blue is reference, so it's just the base model where we sample response and we compare it to the response in the data and we sort of do win-win with that. There's like best of n, there's PPO, PPO++, and DRPO. So we saw that like that observation that we saw was the data from the underlying data in the responses in the data set was better than the responses that come from the pre-trained model. So when we use that, performance should go up. And that's exactly what we see here. And so in general, algorithms that use resets perform better than those that do not. Why? Because we're helping with exploration. And DRPO consistently performs all baseline algorithms. Now the catch is that we're assuming that that data set that they're resetting with is better than the data set we're getting from the pre-trained model. And this is like kind of depending on the task on which one you decide to choose. But you first have to assess which, like, is it the data set responses or the pre-trained model responses, which one is better? And once you decide on that, then you know which algorithm you should be running. And so we also did sort of an ablation where we looked at reward model trade-off and KL trade-off. And so we see here that DRPO consistently achieves better reward model score with lower KL than PPO for most of the points for KL. And so we also ran experiments on the anthropic helpful harmful tasks where the model tries to produce an engaging and helpful response to dialogue sequences. And so an example of something how the data set looks is like you have a human and says like, what do I do if I crack my molar? And then like there's a chosen assistant and a rejected assistant based on responses. And so the results for the anthropic task looks like this. We compare against SFT, DPO, PPO, and DRPO. And the x-axis is model size. So we want to see, as we increase model size, how does performance against all the baselines look like? The y-axis is GPT-4 win rate. And so the first thing I want to point out here is that online methods outperform offline baselines. And the second thing is that DRPO outperforms all the baselines at every model scale. And this is the basic, the gist of what I'm showing here is that like, if you do have really good data, you can use it for exploration, and it should help you. At least that's what all the experiments that we've seen have shown us. And so in summary, resetting from offline demonstration data enhances performance. DRPO is provably efficient and improves upon PPO++ in theory. And DRPO is as simple as PPO and requires no additional computation. Any questions? Yeah.
Have you tried to use the data that got generated by your DRPO
your methods and do SFT on this?
No.
Okay.
No. There's like...
Because that could be interesting to see if it's like the RL or the data generated through RL that actually is the important.
Yeah, that's a good question. Like, they're like... So like, we like had momentum and then the student that was working on this graduated. And so all our momentum just like... but like we had like questions like this. We had like questions like what exactly is going on here? Like can we just do this over and over again? Like we see the bump in performance, right? Now we have better data. Can we repeat this? There's like a lot of these questions we were interested in doing, seeing like how can this help? It's like very similar to like go explore, things like this. Yes.
Suppose you had not just one agent, but you had multiple agents.
Mm-hmm.
Same Montezuma's revenge. Can you exploit that data to kind of intelligently do these resets? Right. And
Yeah.
How would you elaborate it?
I mean, if you have multiple agents, like playing Montezuma's Revenge, and you were just putting that data into a single pot, and then distilling that down for exploration for a policy to learn on, it's very, very similar to Go Explore. Like one of the, like, all in the beginning of the talk, it was like Montezuma's Revenge. There are two ideas that actually kind of solved it. One was learning from a single demonstration data, which is just basically saying you have a curriculum. You have one demonstration data to solve the problem, and you just start at the end, reset at the end, solve it, and keep moving backwards. And then Go Explore is something like this. Like you get a bunch of exploration data, you use that for resetting, and you do curriculum on it.
So it will perform better than all the schemes over here, that you've shown, like PPO, PPO plus, and the DRPO.
I think so. We haven't ran it yet, but it's possible that, I mean, as your exploration data gets better, then like the policy should be getting better as well. It seems plausible. But so the one thing I want to point out from the summary is that DRPO is as simple as PPO, and it requires no additional computation. But all of the recent RL algorithms are about like reducing the computation overhead of PPO, right? It's like I want to remove my value function and do rollouts with that and estimate the value function, so I don't have an additional model in the on my GPU. Or there's like other ways that like people have been thinking about trying to reduce computation of running RL for language models, right? And DRPO doesn't sort of address that. It's just helping with exploration, right? So far we talked about resetting with reference policy, talked about resetting with demonstration data, and now I'm going to talk about resetting with the current our current policy. And the idea is that, yeah. Does it learn faster? That's a good question. I don't remember the learning curves. I just remember the final performance. But I can definitely look it up and let you know offline. Yeah. And so the question now is that if we reset with our current policy, can we reduce computation? I mean, like, can we remove the need to have a value function? Can we remove the need to have additional things on the GPU, but still like have an RL algorithm that has some guarantees and performs well in practice? So the question here is very simple. How can we reset, but use, how can resets be used to make RL algorithms more efficient in computation and memory? So far we've like resets are great for exploration, but can we use resets beyond what they were used in the past for helping with exploration? Can we use them to solve a different problem that we know is a problem when we do RL for language models? So if we go back to our maxent RL objective, we write down the objective, looks like this. We would like to find the argmax policy that corresponds to having high reward subject to this KL constraint. Now we know that the closed form solution from Brian Zebra's paper looks like this. It says like our next policy can be written in terms of our previous policy was a prior exp times some weight of the reward divided by some normalization constant, right? And then from there, we can rewrite this reward in terms of the policy from the DRPO paper, which is pretty cool observation, right? And then everyone probably knows where I'm going next. We can assume that the reward function follows Brantley-Terry, and we can just plug that reward function into this Brantley-Terry formulation. And so, like, why is this nice? This is nice because we've, like, removed the need to, like, learn a reward function and then learn a policy. We like just do it all at once, right? We don't need a value function, and we don't need the reward function in memory. It's a very efficient algorithm. But there's a caveat here. We assume that the reward function is Brantley-Terry, and like not all RL reward functions are Brantley-Terry. I mean, there's verifiable rewards. There are like Plackett loose rewards. I can keep naming rewards that exist. There are tons of rewards. Not all are Brantley-Terry. So here's a simple question. If we assume nothing about the reward structure, but instead assume access to environmental resets, like what can we do? What algorithm can we come up with in order to have just as simple as DPO, requires roughly the same memory overhead as DPO, but it's just assuming something slightly different that we know works well for exploration. And so in this paper called Rebel, Reinforcement Learning via Regressing Relative Rewards, we address this problem. And this is joint work with Azalin, Jonathan, Owen, Jason Wen, Goku, Winal, Thorson, and Drew Bagnall. And so the Rebel algorithm looks like this. At iteration t, with policy pi, I'm going to sample hybrid data using resets. So how does this look? I'll sample a prompt from my data set. I'll sample response from my policy. I'll reset back to the prompt, and I'll sample another generation. So 2 generations coming from my prompt, and this reset ability to go back to the prompt and generate another trace is the thing I'm going to take advantage of. And then I'm going to do something very simple. I'm going to take the closed form solution of the reward function and just regress the difference. By regressing the difference, the normalization constant cancels out because it only depends on the prompt. And I get just like simple regressing the relative reward objectives that I'm showing on the slides. And so the one thing I want to point out here is that this mu distribution could be offline data. It could be a reference policy. It could be best of n. It could be whatever you want. And it has a very similar flavor to the algorithm I just talked about. Well, mu could just be your policy where you sample an additional response. You can tuck anything into this mu distribution that you're using in order to sort of regress the difference of reward from. And so the log ratio we can think of as being the predictor for regression, and the reward difference is sort of the target. You want any questions? Does that make sense? So informally, the theory of Rebel looks like this. If we can solve this regression problem well, in that we can drive the regression loss to be very, 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 very small, then we can do as well as a policy that's covered by the training data distribution. Right? So we can drive that loss to be small in distribution. Then we have some guarantees about being as good as any policy that's covered by the mixture of the distribution that we're sampling responses from. Right? It's very similar flavor to the things we just talked about. Like if we assume some coverage, like for PPO++, if we assume the reference policy has good coverage, then things are great. For DRPO, we assume that the data set has good coverage state and trajectory-wise and state-wise, we get good performance. And here again, if we just assume we have good coverage, then we're guaranteed to get some good performance. And so again, we're going to go back to the Reddit TLDR summarization task, where like we're given a post, the subreddit, the title, the post, and we're given human labels. We're going to look at what happens. Now, I would have loved to have PPO++ and DRPO on the same plot so we can see them all, but there were just a lot of things have changed since those two papers and this paper, like base models. There's just a lot of things we learned and changed, so we couldn't go back and move them all forward. So what I can show you is just how does Rebel perform against PPO and iterative DPO. And we have some ablations about different in the paper about different distributions you can use for sampling for mu. And so what I'm showing here is on the y-axis is GPT-4 win rate. On the x-axis, I'm showing two model sizes, 1.4B and 2.8B. And again, so we're going to start with blue. Blue is just base model, a sample response. Look at the response in the data. GPT-4 win rate. You see it's 24.9% for 1.5B and 28.2 for 2.8B. And in green, I'm showing DPO. And we see there's a bump in performance from base model to DPO. And then I'm showing in yellow iterative DPO. I mean, we're doing DPO online. And in red, I'm showing PPO. And we see there's improvement from DPO to PPO, means there's improvement from doing like DPO, which is offline, to like PPO in red, which is online. And in fact, all of the online algorithms in orange, red, and purple all are better than doing sort of an offline algorithm like DPO in green. And across all these methods, we see that Rebel is performing better. And in fact, Rebel is consistently outperforming all baseline across these two scales that I'm showing. But the thing we were after was not performance with respect to like GPT-4 win rate. We were trying to see, could we come up with an algorithm that was like compute efficient? And so what I'm showing here are two plots. One is time, the other is peak memory usage. So offline methods are more efficient, but they yield lower win rate, right? They don't require, the policy updates is very, very low, and the generations is low as well. So offline methods are more efficient, but when we saw in the previous plot that these offline methods win rates were much lower, so there was an inherent trade-off here. And so you have to decide, like, are you willing to trade that off? And we see here, though, that Rebel is more efficient than PPO and is as efficient as iterative DPO. But we saw there was a performance bump from doing Rebel versus doing iterative DPO. And now, once given these initial results, we decided to scale to like a larger model, like 8-beat model, on a more modern benchmark task. And so for here, I'm showing a data set for ultra feedback. The reward model is ARMO. And on the x-axis, I'm showing Llama 3 8B, which is just the base model we started with. There's DPO, and there's Rebel, and there's GPT-4 time step at 0524. And we see across both, this is Alpaca eval, so for both lymph control win rate and win rate, we see that Rebel does outperform the base model that it started with and DPO. So the thing we're after was like trying to like come up with an algorithm that's just as compute efficient, but doesn't make any assumptions about reward. And we see that we came up with it, and we see that it does give us improvement in performance, and this algorithm sort of come with guarantees. And so we also scale this thing to like reasoning tests. So for here, what I'm showing is fine-tuning Quinn 2.5B on the math and GMSAK 8 data set. The reward model is a verifiable reward, and the baselines are PPO, GRPO, and Rebel. And so the thing that I want to point out here is that, yes, the performances are all the same, but the thing we were after Rebel is not technically trying to boost performance. We're just trying to come up with an algorithm that's compute efficient, that we know has good theoretical guarantees and take advantage of sort of these environment properties. And so in summary, Rebel reduces the RL problem to a sequence of relative reward regression tasks. Empirically, Rebel outperforms PPO and is computation efficient, and memory usage. And Rebel achieves strong results for standard language model benchmarks. So I started this talk trying to answer a simple question. How can we develop efficient algorithms for learning maxent RL objectives, assuming access to environmental resets? And the reason why we wanted to assume environmental resets is because we saw for a previously hard problem in RL, the Montezuma's rhythm problem, when people assume access to environmental resets, meaning that the environment is resettable and the transition function is deterministic, we saw really big gains in performance. And those gains were coming from exploration, but we also see that now, like, if we do resets, we can get gains in other manners as well. And this observation, not only did Rebel make it, but it's also been observations been made from other papers, such as Vine and PPO. Their papers have also sort of saw that this thing helps. And so in this talk, we talked about 3 regimes for resetting. Resetting with the reference policy to boost exploration. If your demonstration data is slightly better performant than the data you get from your reference policy, then you can reset with the demonstration data to boost exploration. But then we're like, well, not only do we want to boost exploration, like we also want to like reduce computation. And we saw that resetting with the current policy can also help reduce computation as well. So resetting is this powerful trick that if your MDP has it, you should definitely take advantage of it because it can help you solve some problems in which algorithms that don't take advantage of this environment-specific structure are not able to sort of do. So with that, I would like to acknowledge my collaborators, and I'll take any questions.
There are problems that don't really have resets in them. So for example, I mean, you could maybe do, like, you could cast like computer use or like software engineering stuff, like you could simulate it with resets, but like in practice, like you don't want to reset too much, I guess, and especially when you're actually rolling out. So I'm curious if you have like intuitions about things that you've learned from this work and how it might apply to environments that actually you don't want to reset like too much or like at all.
When you say you don't want to reset, like you have a coding problem and you don't want to reset, like you don't want to like reset the.
It could be like expensive, or like if you have like a physical manipulation problem, like with a robot, like resetting could be really expensive.
If resetting is expensive, then I don't think these algorithms will help you.
Oh yeah, I'm just wondering if like from the sort of exploration point of view, if you have thoughts on.
Yeah, I mean, like for like if you have a robot and you have a really good simulator, resetting in the simulator can help you learn a bit there. But if reset is expensive, then strategically deciding where you reset to is a question that I find very interesting. There are a couple of papers along that path of like, because at the moment, like I said, okay, we should reset, and not one time did I say how we should reset. How am I resetting? I'm just randomly deciding a point to reset every time, and that seems to work fine. But if reset is expensive and you have to like be more strategic about where you reset at, deciding on that point is interesting. I have thoughts on it. We can chat offline about it if you're interested. But deciding on where you reset to is very interesting. So that'll help the problem of like, you would like to reset, but it's expensive. So you have to be more strategic about the points you decide on. Yeah. There are a couple of papers along that path. Yeah.
In this entire talk, you didn't talk about advantage in any sense, right? So when you do these resets, right, you are kind of are you trying to work out the advantage of this new exploration versus what you did already? Because in this talk you didn't consider that. Is that to bring advantage into the
That's a good question. Yeah, so in the paper Learn and Generate Better in Your Large Language Model, if you swap the roll in and roll out policy, so if you roll in with your policy and roll out with the reference policy, then when you roll out with the reference policy, you're using the reference policy advantage function. But when you roll in with the reference policy and roll out with your policy, you're using your own advantage function. So that swap, I didn't talk about advantage because I'm just using my own advantage function at the moment. But when you swap the roll in and roll out policy, you get a different advantage function. and you get kind of different guarantees and guarantees that I mentioned. And it's a completely different algorithm.
Questions? All right, then let's thank our speaker again.